Hi, I'm Olivia, everyone's favorite math teacher, and in this video we're going to talk about another application of linear approximation, something called Newton's method for finding the zeros of functions. So this is Newton's method for finding zeros of functions. Now, this came about because we'd had the quadratic formula and we had the cubic formula, and people were wondering, is there a fourth degree, a fifth degree, or a sixth degree formula for finding the zeros of polynomials? And it turns out, no, there's not for fifth degree and above. We do have a fourth degree formula. It's just a bit complicated. And what we do know, though, is that if you have an odd polynomial, you will have at least one real zero. And if you have an even polynomial, you will have even numbers of zeros that might be real or complex, depending on whether or not your function intersects the x-axis. So the concept behind Newton's method is that when we are using linear approximation, we know that at the point our line converges with the graph, the function. And when we're close to the point where we're taking the derivative, we know that the linear approximation is close to the function. So his idea was that, well, wouldn't that also mean that the zero of our linear approximation is close to the zero of our function when our derivative is also close to that zero? So the idea here is that we find a value somewhere that's a good place to start. And we take that approximation and we walk backward on the line until we hit the x-axis. And we use that zero as the new x to look for a new, hopefully closer value. And then we use that one to do it again and again, with the goal of every time we take a linear approximation, the f of x is getting closer to wherever the zero is. And our x is also approaching. So what we're doing is sliding along this graph and bringing this x0 in until finally we're close enough. And just like any approximation of an irrational number, we have to decide what we want our degree of accuracy to be. So how many decimal places out we want to be accurate to, so that we know when to stop. Because honestly, we could keep going like this pretty much forever if we are using real values and not with approximated, or rather if we're using approximated values rather than real values. So if we're not putting in like the square root of 2 and pi, we're using decimals, we have to decide what point we want to stop our decimalization. And through just continual iteration, we'll eventually get there. Now, there are three places where this could fail. And the first one is actually pretty easy. We kind of mentioned it earlier with the polynomials. And that's if you have a zero that isn't a real zero, it's a complex zero. Meaning that somewhere where your derivative is zero, but your graph doesn't cross the x-axis. And the reason should be pretty obvious from the formula, because if your derivative is zero, but you haven't crossed the x-axis, you can't continue to iterate because you'd be dividing by zero. Now, the other place that this can fail is a little trickier, because you'll actually get a solution, but maybe not the solution you're looking for. And that's if you have a couple of zeros that are reasonably close together, and you happen to pick an x that does not find one of your zeros. It kind of overshadows it, right? So in this situation, we picked an x here looking for this zero, but we picked an x that was convenient for calculation, but not close enough to where that zero was. And so what happened was we ended up finding this x, which got us here, which does get us closer and closer to this zero, but that's not the zero we were looking for. So we found a zero, but not the zero we wanted, right? And the third place that this could fail is when you're doing your iteration. If you happen to get a function where, for some reason, you are jumping and it ends up iterating out. And this usually happens when you do have another one of those complex zeros, where you've picked an x that gets you onto a track on your function, where you end up being further out because you've jumped past another zero that wasn't on the x-axis. You'll see examples of that, but the easiest way to tell is that your iteration ends up diverging, meaning that the numbers are not approaching the same number. Either they're just bouncing back and forth, or they're getting further apart. And then you know, okay, you're on the wrong track, stop, and either try to find another one or end up using another method. So let's see how we can actually put this to work. So here's an example of Newton's method in action. Now, our problem is find the zeros of 3 cosine x is equal to x plus 1 out to 6 decimal places. The first thing you're going to want to do when you approach a problem like this is estimate how many zeros you expect there to be and what would be a good starting guess for those zeros. A value close to where those zeros are going to be that will be pretty easy for you to start your process. Okay? Now, with one like this, graphing it is pretty easy because we know that 3 cosine x looks just like cosine x, just tall. And we know exactly what x plus 1 looks like. So I can easily graph 3 cosine x by knowing, okay, well, its zeros are at pi over 2, negative pi over 2, and I know that it peaks at 0 and it has its trough at pi and negative pi. Then when you graph your line, you know roughly about where your zeros should be. So this tells me that I'm looking for a 0 somewhere around 1, probably a little behind it. And you can check that, by the way, by simply plugging 1 into here. And you'll note that 3 cosine x is close to x plus 1, but lower. So it matches my idea here, which is that this one is lower than this one. Pretty good there. And you could check the same thing for 2. So you can check these values to see if they are close matches in here by simply plugging those in. Okay? And that'll let you get, okay, I'm reasonably close to where my zeros should be. Okay? At that point, you just start the process. Now, the first thing you're going to want to do is set this up as a single function equal to 0 because I'm looking for zeros. That's always the first thing we do, set it up in the standard way. Set that equal, that's our f of x. Then we find our f prime of x. So, easy derivative, not a big deal. And then we set up our equation. So here, I'm only going to do the first one because it's the exact same process for the other two, and you're just going to be using your technology here. You're going to be plugging numbers into a calculator. The hardest part of this is figuring out how many x's you need and which ones to use, and then checking them. Once you've got this done, this part is just manual labor. Okay? Now, we go ahead, we put the 1 in, and we get our first approximation is 0.89243795. We take that, we plug it back through to get our next approximation, our x3, and we get 0.88947289. Now this is where we want to check things. We knew that we would need to be going back to the left because of the way that our graph looked, and that fit how it looked up here. Okay? And sure enough, if we look, we started at 1, then we're at 0.89, then we're at 0.88. So we are moving gradually backward, which is what we expected. So far, so good. So as long as we continue to converge to a value, we should be good to go. We go to x4, plug in the x3 up into here, and we get 0.88947040. There was some more stuff over here. We're only looking for 6 digits, so I went out to 8 digits. So we go to x5 and we get 0.88947040. Same thing we got for 4. Again, there were more digits out here, but I only went out to 8 because we're looking for 6. So that means I found a good approximation for 6 digits out. Okay? And if you plug this number back in, if you want to check it, simply plug that number back in and you'll see that, yeah, those are pretty close to each other. Do that same thing for x equals -2 and x equals -3. And as long as you are getting to a convergent value, you're good to go. So next up, I'm going to give you a couple that you can work on your own. And as usual, the answers will be after the outro. So I hope you found this overview of Newton's method helpful. And if you have any questions, feel free to drop into the comments or join us on Discord. If you happen to be one of those people who asks, why would I learn this when I have Desmos? There are 2 responses. The first is, how do you think Desmos got to how it is? And the second response is, because we'll be coming back to this idea when we look at series, and knowing how at least one of these works in a way that is very easy to understand will help when you start looking at slightly more difficult series. And as usual, the answers to the exercises are going to be after the outro.